This is lecture 26. I'm recording this from a conference, so there might be interruptions, which I'll try to manage. If not, I'll re-record this. We're continuing on the path of frequency response analysis. And a major claim that I made was that if you have any linear system with any transfer function that's given, and you have some oscillating or harmonic input given by some magnitude multiplied with a frequency, an oscillating input like sine of omega t, then the output of the system, which is basically how is the system's response going to be to this input, will be whatever is the amplitude multiplied by some magnitude gain given by the magnitude of t of j omega, where we're just replacing s with j omega. And so that becomes the updated amplitude. And then there is a sine of whatever was the same input, so omega t, plus some phase angle difference. And this phase angle difference is also obtained by using the transfer function, substituting j omega, and then looking at it in the phasor representation so that we can obtain the angle difference. And as a reminder, what that means is if you have a set of two complex numbers, and you're taking the ratio between them as a plus jb divided by c plus jd. We're basically converting this to an a1 e to the power j phi 1, and you're dividing it with a2 e to the power j phi 2. And this gives us the advantage of quickly computing the ratio between these complex numbers. So in this case, it would be a1 over a2 e to the power j phi 1 minus phi 2, right? And what we were saying was that this part over here, whatever you obtain, if this was a transfer function, this would be the magnitude gain, and this effectively is your phase angle. So without going much into refreshing all of this, let's just look at an example so we can quickly gather our thoughts on, or rather recollect what we had looked at. So let's say that we have a transfer function that's, let me just find an example. Yeah. So as an example, consider 6x dot plus 2x is equal to 15 f of t. So this, you should immediately identify that there's a first order system. And the idea is that if f of t is a steady state, sorry, if f of t is an oscillating input given by, say, 3 sine of 2t, then what that means is you can use a transfer function of this system to this input to obtain what would be the steady state response. Let's do that now quickly. So general practice, always a good idea to convert to standard forms when you start using these laws and whatever is the mathematical representations given to us by mathematicians before us, and we're just using their results, right? So it's always good to convert it to standard forms. So in this case, the standard form would be 3x dot plus x is equal to 15 by 2 f of t. So this here, this term is the gain to whatever is the input, and it'll feature in the transfer function, right? So now if you were to take the Laplace transform, you would get 3s plus 1 times x of s is equal to 15 by 2 times f of s. Reminder that there is no initial condition, so we don't care about that. And the transfer function then would be given by t of s, which is x of s over f of s, which results in 15 over 2 divided by 3s plus 1. At this point, we can immediately say that given any kind of an oscillating input, we can obtain exactly what is the output without doing any of the detailed Laplace transforms. We're not going into mathematical proofs of why, but you can trust me that it works. And so now that we have this transfer function, the idea is that if you're expected to recognize the way that the system, or rather define exactly how the system would respond to such an oscillating input, you just supply the input as t of j omega, where this omega is basically the frequency of the oscillation. For now, we're going to keep it as j omega, and then we can substitute it later for this illustrative example. So in this case, it would be 15 over 2 divided by 3j omega plus 1. And we can then have the angle associated with this as the phase angle being tan inverse of the numerator complex number. So in this case, 0 is the imaginary part and 15 by 2 is the real part, minus tan inverse of the complex part, which is c omega divided by 1, which is the real part. So I hope it's clear that this omega here stands for this frequency of the oscillation. If we now substitute these values, this goes away, and then we are left with minus tan inverse of 6, which is equal to minus 1.41. So that's one part of the response from the system. The other part is the magnitude gain. So in this case, we are looking at finding out what is the magnitude of the phasor that's associated with the ratio of the numerator with the denominator. In this case, it's quite straightforward. In the numerator is 15/2, and in the denominator, it is 3 omega whole square plus 1. We're looking at the complex part, so the imaginary part of the complex number squared plus the real part of the complex number squared. So in this case, it results in 15/2 divided by, in this case, when we substitute, you'll get root over 3 times 2, so that is 6 squared plus 1. That's a number which is equal to um, something which I basically calculated beforehand as a complete response as x of t is equal to c magnitude of t of j omega sine of 2t plus the phase angle difference. And if you now substitute the values that we found, you would then have sine of 2t minus 1.41. And this is the thing that I calculated beforehand. So this is equal to 3.69 sine of 2t minus 1.41. So we're able to find this without doing all the Laplace transforms and the inverse Laplace transform and then bring it back to our domain and so on. And effectively, as based on this pretty big result, we are now showing that given an input of 3 of sine of 2t to a system whose transfer function is given by 15/2 divided by 3s plus 1, that being the transfer function, it gives us an output of 3.69 sine of 2t minus 1.41. So amplitude has been multiplied with something. This is the resulting amplitude, and the gain is what we had calculated here. Whatever was the oscillating frequency, 2t exists as it is, but now there is a phase gain, which in this case is minus 4.1. Maybe I shouldn't say phase gain because gain is used for multiplication. There's a phase angle given by minus 4.1, 1.41. Okay, I hope that was clear. And with that, let's move to a simple second order example. So second order example where we're going to use the same idea, and you see that even though it's now a second order system, the steps do not change at all, and this can be used for any linear system. Okay, so we're looking at the system given by 4x double dot plus 8x dot plus 20x is equal to f of t, where f of t is given by 4 sine of 2t. And in this case, again, let's take it to a standard form. X double dot plus 2x dot plus 5x is equal to 1 by 4 f of t. Now, we don't need to really understand if it's underdamped, damped, overdamped, because there's a forced response and we can directly obtain the output of the system by using the learning outcomes of the last class. So let's obtain the transfer function by taking the Laplace transform. We get s squared plus 2s plus 5 x of s is equal to f of s divided by 4. And that gives us t of s is equal to x of s over f of s, giving us 1 by 4 over s squared plus 2s plus 5. Cool thing is we don't even need to factorize this. We can, if you're looking at the system response, we're just interested in substituting instead of s, we substitute j omega. We obtain 1 over 4 divided by, now j omega whole square plus 2s is replaced by j omega plus 5. Give me a second. And because we know that j square is equal to -1, we use that here to have 1 over 4 divided by 5 minus omega square. That comes from j square being -1 plus 2 omega j. And depending on the application, you could go ahead and find what is angle of t of j omega for omega remaining as a parameter. But since we know what is omega, and I'm just trying to show you an example, you can then just substitute it here to obtain 1 over 4 divided by, it's 5 minus 2 square, so that's 1 square, plus 2 omega is 4j. Sorry, I should not have put this here. So it's basically t of j with omega substitute as 2, and the phase angle is given by the difference of the tan inverse of complex part being 0 divided by the real part being 1 by 4, which goes to 0, minus tan inverse of complex part divided by real part. So 2 omega, which in this case is 4. So I should probably point here, 4 over the real part divided by 1. And this gives me minus 1.32. And we have the magnitude of t of j2 as what would obtain if you took the magnitude of this phasor and this phasor. So in this case, it'll be 1 over 4 divided by under root 4 square plus 1 is equal to 0.06. Now, all we have to do to obtain the system response is we write now x of t is equal to whatever is the amplitude, so 4 multiplied by the magnitude gain, which is 0.06, sine of the same frequency, so 2t, plus the phase angle, which happens to be minus 1.32. And this will give us our response directly as 0.24 sine of 2t minus 1.32. So I hope you see how elegant this method is to find the response of a system to any kind of oscillating input. So I hope this example and the first order example give you a good sense of how to use this realization. But there's a very profound mathematical tool, because if we have some input a1 sine of omega 1t coming into some linear system with t of s, it gives us a1 mod of t of j omega sine of omega 1t. So this is omega 1 plus the phase angle, which is given by angle of t of j omega 1. And I think you can see what's happening now. I'm trying to use the principle of superposition. So we have another input coming in. It's going to be another component of the output given by this sine of omega 2t plus the phase angle associated with omega 2. And you can keep doing this for all the different components of the input, and the principle of superposition will give you the components of the output. And of course, x x of t is equal to this guy plus whatever's here plus whatever's there, and so on. So it's x1 of t plus x2 of t, and so on. So those of you who remember what Fourier transform is, it means that if you have, say, some signal that looks like this is generally what you will find in when you take actual measurements of vibrations and so on. It's not something that you can directly call as something like 3 sine of 3t, and that is the signal that you have. It's usually never the case, and especially if it's like uh, a system that's experiencing an earthquake or some frequency that is not coming from some oscillatory response. If it's something that um, happens due to some complex behaviors, there's going to be so many such uh, peaks and valleys that do not match such a sinusoidal wave. This will be considered to be a combination of one sine wave of a certain amplitude plus another sine wave of another amplitude and another frequency plus maybe another one like this. And all of these combine together to give you this overall frequency. And by finding out what is this and what is this for the system that you're analyzing, you can then obtain, if you have it parametrically defined, you can just provide what is omega 1 and what is A1, and you can immediately obtain what is the output caused by this guy, that guy, and multiply and add them up together to obtain what is total system response. And as you can imagine, having a very high magnitude gain will result in larger fluctuations, larger deflections, which are associated with mechanical strain and failure. And so, a lot of the times, you're trying to find which among these frequencies that you're expected to experience will result in a high magnitude gain. So I was kind of alluding to, we're interested in finding out which among those frequencies and yeah, which among those frequencies will result in a magnitude gain that might make your signal really large and so on. So to do this, we use a method of Bode plots. Bode plots, so it's spelled BODE plots. And I think since we are from the Ohio State, we should always correct anyone who calls it Bode plots, because the person Bode studied at the Ohio State. He made such a huge fundamental contribution towards the field of system dynamics. And we should never let anyone mispronounce his name and call him Bode when it's a Bode plot. Okay. But based on the motivation of looking at Fourier series and how these input signals are composed of so many different signals that add up together to get that overall signal, there are two things that we're looking at. So one is the Bode magnitude plot, which basically compares the magnitude gain. So on the y-axis, let me just draw it. So on the y-axis, we have magnitude gain. And on the x-axis, we have the omega, which is in radians per second. Now, something that I need to correct here immediately is that even though we're studying the magnitude gain, we do it in a unit called decibels, which, if you're familiar with acoustics, or maybe you have a car with an aftermarket exhaust and you're worried about how loud that exhaust is, the decibel is a unit of measurement associated with how humans perceive vibrations and sound and so on. It's the most natural scale that captures human perception. And so instead of just plotting the magnitude gain, we plot it in decibels, which basically makes it 20 log to the base 10 of the magnitude gain. Okay, so um, we are going to be using this as a y-axis, and we're going to have units that look like, we're going to have ticks that look like this. Okay, that's the y-axis. And on the x-axis, we will have radians, but as you can imagine, the world is composed of some low frequency experiences and very high frequency experiences. And the low frequency ones contribute to signals that do not die out very quickly, and the high frequency ones do. So if you want to remember that, think about how there's, about how in the wild, the lion's roar, because it's so deep, can be heard so many miles away, or a whale's whistle, because so deep, can be heard from so many miles away. And by deep, what we mean is low frequency sounds. While things like birds chirping or other sounds that are high frequency, they die out very quickly. And we're going to see that in the plots that we analyze. But because there's such a big range of these frequencies, we do not show it as the scale that we are commonly used to, which is just, it's like increasing by 1 unit. Instead, what we do is we use a logarithmic scale, which is instead of 0, we have 10 to the power 0. Instead of 1, we have 10 to the power 1. We have 10 to the power 2, 10 to the power 3. And the other direction, we have 10 to the power minus 1, 10 to the power minus 2, 10 to the power minus 3. And if you're a little observant, you'll notice that this will never go negative in the way that the scale is drawn. That makes sense because frequencies don't ever have there's no real physical meaning to a negative frequency. But the important thing to note here is that these gaps, which I probably didn't draw very well, I'll just do it again, are going to be the same. So you need this distance to be the same as this distance to be the same as that, and so on. But instead of it being, an additional of like something like 10 as an addition every time, it's instead a multiplication. So if you're going from here to here, you're multiplying by 10. If you're going from here to here, you're multiplying by 10. You see that? So this is a logarithmic scale. While if you've been looking at, I mean, all the graphs that we've been looking at are something that looks like, 1, 2, 3, 4, and so on. So here we're adding one, and so on. Here we're adding one, but it is in the exponent. So it's like -2 is being added to -1, add 1 to obtain 0, add 1, but it's all on the exponent. And this is why it's called a logarithmic scale. Okay. So kind of just to build an intuition on what you are going to see in the Bode plots, think about how I said that low frequency sounds will exist for long distances. It does not really die out, as in the amplitude does not die out, as much as high frequency sounds will die out and they will decay, and you will not hear it from a far distance. Or think about why the light in the signal is the red light when you want it to indicate that you have to stop. Because you want that very critical information of you have to stop to exist even when there's a lot of scattering happening from the mist, or maybe there's smog or something. Red light has the lowest frequency. And so just try to remember that low frequencies will end up existing for longer, or the system does not cause as much decay. So we're trying to find that kind of relationship through a graph, and just if you've been thinking about what this graph would represent, it'll be something that has, something like a flat line here, and then it goes down. As the frequency increases, the magnitude gain becomes less than 1, and it starts to decay. So that is one of the plots, and the other plot is the uh, what is it? The phase angle plot. So sorry, my pencil seems to not work. Yeah, the phase angle plot psi. And this one, because it's not something related to frequencies, we do not use decibels. But yeah, for now, let's start with the magnitude plot. And to keep things standard, we're going to start with first order system, whose transfer function is given by, say, T of S is equal to 1 over tau S plus 1. Okay, so there is a first order system, but it's not in the standard form because it has a gain of 1. Okay. And the reason why I do this is so I don't overwhelm you with information in the very beginning and we can kind of build an intuition as we go forward. But I should probably have marked this as capital T instead of tau. So we're interested in how does the magnitude gain change with omega, right? And because we are looking at omega changing, we'll keep it parametric. So I'm going to start by substituting S is equal to j omega, and we obtain very easily 1 by tau omega j plus 1. And very easily, again, we obtain the magnitude is equal to 1 over root over 1 plus tau omega whole square. Okay. And as I mentioned, because of the way that we perceive these vibrations and because it makes sense for the analysis of vibrations as a whole, we use it in decibels. So we are interested not in plotting the magnitude of T of j omega, we're looking at 20 log to the base 10 of T of j omega. And that gives us, just rewriting it. Okay, so if you remember your log formulae, this basically means you're doing 20 log of 1 minus 20, and let's just keep the base as well. So it's clear that it's not like the natural log. So 20 log to the base 10 of root over 1 plus tau omega whole square. And if you remember, log of 1 to the base of anything is 0. And if I were to rewrite this, I could rewrite it as this much raised to half. And if you remember your log formulae, because there's an exponent on the term inside the log, that exponent can be taken out, so it comes here, which means this can be written as minus 10 log to the base 10, 1 plus tau omega whole square. Okay, so we're basically interested in plotting this, and I'm just going to put in a placeholder for what the plot should look like, or rather the place where we're going to fill in the plot is in dBs. We're going to do 20 log to the base 10 of the magnitude. And what this means is we now need to find the relation for this function with omega. This is pretty, if you have an intuition for how to make plots, you're basically looking for these characteristics of the plot as the x-axis goes to a very small number. So like what is the asymptotic behavior as omega becomes very small or as omega becomes very large. So that is one of the aspects of plotting a graph. And you basically find how it behaves. And if there's some transition between them, you want to find what is that transition as well. So one case we can look at is what happens when omega becomes really small. And in particular, since omega is going to be greater than 0, we can look at the case when omega is less than 1. Because if omega is less than 1, then omega square is going to be really small. And so this part of the component within the log will become really small. So let's look at case 1. Omega is much smaller than 1. So 20 log to the base 10 of is equal to minus 10 log to the base 10 of 1 plus whatever is the time constant. This omega is something like 0.00001, let's say. So if you square it, it'll become something like 0.0000001, which means this becomes very, very small. So this is going to be like having this within the log. So since log of 1 to the base of anything is 0, this becomes 0. So that means that for omega much less than 1, and if you remember, it's like we have, 10 to the power 0, 10 to the power 1, 10 to the power 2, and so on. And then 10 to the power minus 1, 10 to the power minus 2, and so on. So as we go much smaller than 1, so that's like we're in this region, the value that's going to be plotted on the y-axis is 0. If I just mark that, I have 0 dB, and that is one clue that we have. And we can say that this approximation is valid for omega much smaller than 1, but for some reason, it's going to be somewhat along the 0 dB horizontal line. Let's look at the other case where omega is much larger than 1. So it's like we're going out here towards infinity. This here sets up case 2, omega much greater than 1. So in this case, if you look at what's inside the log, this term becomes really big. So if omega is equal to, let's say, 100, then omega squared is going to be 10,000. And it's like 10,000 multiplied by the time constant squared gives you something, let's say 40,000. And then whether there is that 1 or not doesn't really make a difference because this 1 is so small compared to this. And so we can then write that 20 log 10 j omega is approximately, and I should probably correct this. Instead of putting an equal to sign, I should say it's approximately. Okay. So it's approximately minus 10 log to the base 10 of tau omega whole square because the 1 doesn't contribute barely anything compared to what this contributes. And so for very large omega, we can say this is approximately this. And now if I take the 2 outside, you get minus 20 log to the base 10 of tau omega, this much dB. So we are getting something in terms of tau and omega, and for the most part, it is in the form that we like, so it's 20 log or something. So this here is going to be, let's see, if we put omega is equal to, say, tau by 10. Let me write that again. So if omega is equal to, actually not tau by 10, let's say it's omega is equal to 10 tau, or 10 by tau, then what we're going to be plotting is minus 20 log to the base 10 of tau omega becomes 10. So then we have minus 20 dB. And if omega is equal to, say, 100 by tau, then you would have minus 20 log 10 square to the base 10, which is like minus 20 log 10 to the base 10 multiplied by 2, right? And log 10 to the base 10 is 1, so there's minus 40 dB. So we see here that if omega is now written in terms of 1 by tau, there's an advantage because we get nice round numbers. It's kind of how most of the plotting work happens is we just try to look for characteristics in the function and you exploit that. Let's look at what happens when omega is equal to 1 by tau. In this case, even without making this approximation or that approximation, let's just put in the values. You get 20 log to the base 10 of j omega, the magnitude of t of j omega is equal to, we had found is minus 10 log to the base 10 of 1. So we're looking at this one, okay? 1 plus omega tau is now 1 squared, so it's still 1. It's like minus 10 log to the base 10 of 2, which I've calculated beforehand to provide us minus 3 And this is all in dB. Okay, so we have many clues at this point. At omega is equal to 1 by tau, and now I'm gonna plot this here. And I'm also going to remove this, and there's something you will see in these Bode plots is you write everything in terms of 1 by tau simply because it is advantageous. So if this is 1 by tau, this is 10 by tau, this is 10 squared by tau, then you would obtain at 1 by tau, you will have 0. From 0, you're going down to minus 3 dB. So there's 1 point here, right? There's nothing to do with poles and zeros. I just marked it with a cross. Absolutely nothing to do with poles and zeros in what we're plotting, okay? Um, and at 10 by tau, we found that it is minus 20 dB. This here is 3 dB. So let's say this is, sorry, minus 20 dB. That's what we have here. And then let's say this is minus 40 dB for that here. So it's like this is the asymptotic behavior as omega increases to a very large number. And this is how omega behaves as, sorry, this is how the magnitude behaves as omega becomes a very large number. And this is how the magnitude behaves as omega becomes a very small number. And there's a transition point happening at 1 by tau given by this. So if you had to sketch out how the Bode plot would be, it would look like this. So for small omega, it's following the horizontal line at 0. At 1 by tau, it is 3 dBs below 0. So it's at minus 3 dB. And then after that, it asymptotically follows this curve, which, if you notice, we've dropped from minus 20 to minus 40. So this is a 20 dB drop in what we call from 10 to 10 square. We call it a decade. Don't worry about taking the notes. I've written all of this quite neatly and it's available to you. But yeah, so this is how you'd obtain the Bode plot for a first order transfer function, where the gain is 1. So important clause, first order system with gain 1. The reason why I did that is so that we can look at this very carefully, understand how we can plot the Bode plot for magnitude, and how 1 by tau becomes important simply because the function's within the logarithmic term. Okay. So with that, I'd like to take it to the real, or rather the standard form of the transfer function for a first order system, which is given by T of S is equal to some gain divided by what we've been looking at as tau s plus 1. So in this case, your magnitude gain becomes k over 1 plus tau omega whole square, right? It's quite similar. And if you were to do, 20 log to the base 10 of this magnitude, you would obtain, you can write it out as 20 log to the base 10 of k minus 20 log to the base 10 of the denominator term using a logarithmic formula. Or if I were to rewrite this, I would have it as 20 log to the base 10 of k minus, and actually I'm going to write as plus minus 20 log to the base 10 of 1 plus tau omega whole square raised to half. And using another logarithmic formula, I would take the half out to obtain minus 10 log to the base 10 1 plus tau omega whole square, which, if you notice, this guy right here is exactly what we've been studying. And so this has a Bode plot given by this. So that means I can immediately sketch this. And this is just like you should just know that all the body magnitude plot means is a sketch that looks like this. dBs, start with 0. You draw something like this, draw something like this. You mark out that it's a 20 dB drop per decade. And we say that at this transition point of 1 by tau, there is a reduction of 3 dB. Okay. So you mark here minus 3 dB and you sketch with a thicker font or a thicker nib. Sketch something that looks like this. So asymptotically, it'll follow the horizontal line as omega becomes really small, and asymptotically, it'll follow this line with a slope of 20 dB per decade as omega becomes really large. That's it. And for this guy here, we then have basically it's just a number, right? So there is something like say 4, because k is a number, and you just do 20 log to the base 10 of k, you get something like 4. And so you have another plot here, which is basically this guy here. It's just a flat line because it does not care anything about the omega. So whatever is the dB. So I gave the example of 4, but I'm just going to write here 20 log to the base 10 of k. It's a horizontal line. And these two add up to give you the final. So this plus this gives you the final, which is basically just look at every point on the x-axis. If you take this point here, it's somewhat at 0 horizontal line. Here, it's always going to be at this 20 log to the k to the base 10. So it's basically like you're shifting this up to this value. Okay, so I'm just going to draw the final graph. It's going to look something like this, where we have here 20 log of k to the base 10 instead of 0. And if I'm trying to show exactly how much is the drop happening here, over here at 1 by tau, this graph crosses the vertical with a 3 dB drop from the original position. And here we have a 20 dB drop per decade. So that is the Bode magnitude plot that you would have for the standard tensor function as shown here. And that is basically it. So it conveys a lot of information. It says that when your frequency is less than 1 by tau, it's basically the frequency, right? Um, and so with that, we've obtained the Bode plot for the magnitude for a standard first order system given by this transfer function. And what it means is that because of the gain, there is some contribution of the gain to the magnitude gain overall. And it is completely independent of the frequency. But because the first order system, this plot here shows us that as omega increases, this whatever is the magnitude gain contributed by the first order system, it comes down. And in the beginning, for small omega, this contribution is basically 20 log to the base 10. So it's 0 dB, which means that the amplitude is not affected as much as when the frequency increases, the amplitude is reduced, which is basically the phenomenon that you notice in real life as well, where when the frequency increases, the amplitude of the sound that you hear, it dies out much quicker. Okay, so I hope that makes sense. You might be asked to be able to sketch this in the exam or maybe the assignment. Of course, you won't have to prove any of this. Maybe the thing I will ask is for a given transfer function, sketch the Bode plot, and effectively you're just going to do exactly this thing, only that the tau will change, and in this case, the k will be affected. Okay, I hope that makes sense. We can probably also address the phase plot in the time that I have left. So the phase plot, as I mentioned, is the comparison of the phase angle with the omega. So this here is the y-axis is just angle t of j omega. There's no fancy decibels or anything. It's just radians, and so you can call it phi maybe. And here we're looking at omega. So if we have that t of j omega is equal to, we found it as minus tan inverse of omega tau earlier. What we're looking at is, angle of this is how is this affected by omega? And so again, we're looking for things like asymptotic behavior, which basically means what happens when omega is really small. So if omega is much less than 1, then this becomes a really small number, and so it's approximately minus tan inverse of 0, which is basically 0. So it means that you would expect that uh, as omega is really small, it'll be following this horizontal line of 0 radians. And then as omega is really large, this becomes a very large number in the order of infinity. So it's minus tan inverse of infinity, which is basically minus pi by 2. So that means as omega is really large, this follows this line here, where it intersects the x-axis, the y-axis with minus pi by 2. And again, because we see this as what's inside, you should intuitively at this point guess that you're going to take as omega is equal to 1 by tau next. And you obtain, not approximately, it's the phase angle is exactly minus tan inverse of 1, which is pi by 4. Minus pi by 4. So when omega is 1 by tau, it takes the value of minus pi by 4. So that there is one concrete point. This here is another um, asymptotic behavior. This here is another asymptotic behavior. And if I were to sketch out how I expect it to behave, something that looks like that. It has to pass through this point. Over here, it approaches the horizontal line. Over here, it approaches the horizontal line. And it has this kind of behavior. So if you're asked to sketch this, the only thing that it depends on is, uh, you know, tau. Because when you look at the phase angle, it's completely independent of the gain, simply because in the numerator, the complex number had 0 imaginary parts. So it was like tan inverse of 0 divided by k minus tan inverse of omega tau divided by 1. And that's how we got this. So there's no dependence on the gain. The phase angle is purely dependent on the time constant. But yeah, this sketch will be perfectly acceptable. You just have to mark this as 1 by tau, and whatever is the tau in the question, you just provide that. In the notes, I'll also kind of give you a little bit of how to estimate, is it going to be above this line or below this line, but not a big deal. I think you can easily see that. So horizontal line, there's a point here. It is going to follow this path. Okay. With that, I'll end today's lecture. Thank you for your patience while I do this virtually. I hope that you guys watch it. I know that 20 students didn't watch the previous lecture. I really recommend doing that. I know that the quiz had an error where everyone saw the marks, saw the correct answers at the end. For this quiz, I'll rectify that. I might be a little late in uploading it, but I'll give you extra time as well for accounting for that. Thank you, everyone.